Hi, so this is take 2 of a video on Lagrange multipliers. They're testing the fire alarm system in building 2, so if I get interrupted, I'm just going to talk through it this time. As our first example, let's find the minimum value of the function x squared plus y squared plus z squared on the surface z squared equals xy plus 4. The first step in solving the Lagrange multiplier problem is to rewrite the constraint in the form g equals a constant. So I can do that here by subtracting xy from each side. So I have z squared minus xy equals 4. And then the left side of this equation becomes my function g of x, y, and z. The second step is the Lagrange multiplier step. We're going to set the gradient of f equal to lambda times the gradient of g. Lambda here is our Lagrange multiplier. So the gradient of f we get by taking the derivative of f with respect to x, y, and z. That will give us 2x, 2y, and 2z. Will be set equal to lambda times the gradient of g. The derivative of g with respect to x is negative y. The derivative with respect to y is negative x. And the derivative with respect to z is 2z. So let's distribute the lambda and then set components equal. Distributing lambda, I get negative lambda y, negative lambda x, and 2 lambda z. And then setting components equal, 2x is negative lambda y, 2y is negative lambda x, and 2z is 2 lambda z. Now notice that this is only a system of 3 equations, but there are 4 variables, x, y, z, and lambda. To get a 4th equation, we're going to include the constraint. And then step 3 is going to be to solve this system. Now, since the system's nonlinear, there's not going to be a standard way of solving it, so you just have to look for either inspiration or maybe a sign of weakness in the problem. Here, this seems to be the weak link to me. 2z equals 2 lambda z. So calling these equations 1, 2, 3, and 4, let's look at equation 3. Equation 3 says that 2z is 2 lambda z. Now you might jump to the conclusion that that means that lambda equals 1, but there are actually 2 possibilities. Let's subtract 2 lambda z from both sides and factor out the 2z. So since one of these 2 factors must equal 0, either 2z is 0 or 1 minus lambda is 0. So that gives us 2 cases to consider. Case 1 is going to be when z equals 0, and case 2 is going to be when lambda equals 1. So let's take those one at a time. So in case 1, lambda equals 0, so let's set case 1, z is 0. So let's set z equal to 0 in all of these equations. Equation 1 is not changed. 2x equals negative lambda y. Equation 2 is not changed. 2y equals negative lambda x. Equation 3 becomes 0 equals 0. And equation 4 becomes 0 equals xy plus 4. Now looking at those top 2 equations, let's see what happens if I multiply the top one by x and the bottom one by y. Equation 1 becomes 2x squared equals negative lambda xy. And the second equation becomes 2y squared equals negative lambda xy. So notice that when I multiply by x and y in this way, I made the right-hand sides the same. So if these two sides are the same, then that means that these two must be the same. So we get that 2x squared has to equal 2y squared. So x squared equals y squared. So either x is equal to y or x is negative y. X equals plus or minus y. So I guess that means we have two subcases. Case 1a will be when x equals y, and case 1b is when x is negative y. Let's substitute each of these into equation 4. That's the equation we haven't used yet. If x and y are the same, and I plug into equation 4, I get 0 equals x squared plus 4. So it means that x squared is negative 4, and there are no real solutions to that. That was a dead end. On the other hand, if x is the opposite of y, then that means that 0 equals, I'll move the minus sign to the other side, y equals negative x. 0 equals negative x squared plus 4. So x squared equals 4, and x equals plus or minus 2. So either x is 2 or x is negative 2. And remember, y is the opposite of x. So if x is 2, y is negative 2. And if x is negative 2, then y is positive 2. And remember, in all of case 1, z equals 0. So in case 1, we came up with two solutions. 2, negative 2, 0, and negative 2, 2, 0. So let's hang on to those. And move on to case 2. Case 2 is going to be when lambda equals 1. I'm going to take lambda equals 1 and substitute it into all four of the equations, equations 1 through 4. Plugging lambda equals 1 into the first equation, I get that x equals negative y. Sorry, 2x equals negative y. Plugging into equation 2, I have 2y is negative x. In equation 3, I get 2z equals 2z. Notice that that doesn't give us anything useful. And lambda doesn't appear in the fourth equation. So z squared equals xy plus 4. So once again, we're going to be working mostly with equations 1, 2, and 4. Let's once again look at those top two equations. The first equation can be rewritten as 2x plus y equals 0. And the second one, if I move the x to the left side, I get x plus 2y equals 0. Well, these are linear equations. We can solve those together. For example, if I multiply the second equation by negative 2 and add them, I have 2x plus y equals 0 and negative 2x minus 4y equals 0. Adding, the x's cancel, and I have negative 3y is 0. So that means that y has to equal 0. And then substituting that back in to this equation, for example, I get that x equals 0 as well. So in case 2, x and y both have to equal 0. To find out what z equals, let's substitute into the bottom equation. X and y are both 0, so z squared equals 0 plus 4, meaning that z is equal to plus or minus 2. So two solutions here, 0, 0, 2, and 0, 0, negative 2. And those are the two solutions that come out of case 2. So now let's plug these 4 solutions into our original function and see what produces a maximum. So let's take f of 2, negative 2, 0, f of negative 2, 2, 0, f of 0, 0, 2, and f of 0, 0, negative 2. And we're substituting into x squared plus y squared plus z squared. So in the first case, it's 4 plus 4 is 8. In the second, 8 again. In the third case, I only get 4, and in the fourth one, 4 again. So the maximum value of the function f is 8, and f takes on this value at the 2 points, 2, negative 2, 0, and negative 2, 2, 0.